Hello, in this video we're going to cover some more derivative application examples. The first question is looking for a tangent line. We have a point and we have a curve. We're going to take the derivative of the function and then we're going to evaluate that derivative at the x value. Which gives us a slope of 28. We know y equals mx plus b. We can use the point to solve for b, giving us an equation of y equals 28x minus 44. Here we're given a curve and we want to find the minimum, maximum inflection points using calculus. Whenever I see this, first thing I do is take the first and second derivative. So we get 8x cubed plus 15x squared minus 16x minus 6. And then the second derivative, 24x squared plus 30x minus 16. Now to figure out the mins and maxes, we set the first derivative equal to 0. Now the first derivative is a cubic function, so I'm just going to use the cubic solver function on my calculator. I get x1 equals negative 2.55, x2 equals 0.97, and x3 equals negative 0.30. Now to determine whether they are a min or a max, you can do one of two things. You can either do the first derivative test and see what is happening around the point, or I always prefer the second derivative test, which is to plug in your x values that are possible min or maxes into the second derivative. So we evaluate the second derivative at x1, which is about 63.6, which is greater than 0, so therefore a min. We evaluate the second derivative at x2, which is approximately 35.7, which is greater than 0, so it is also a min. And then the last one at x3, we get about negative 22.8, which is less than 0, so it is a max. Now to determine the inflection points or points of inflection, we set the second derivative to 0. It is just a quadratic, so we can use our calculator again. x1 equals 0.40, x2 equals negative 1.65. Now, I want the coordinates. So let's list them all out. We have a min at negative 2.55, negative 34.06. We have an inflection point at negative 1.65, negative 18.52. We have a max at negative 0.30, 1.96. We have an IP at 0.40, negative 2.31, and then we have a min at 0.97, negative 6.01. Now all I did was I took each x value and plugged it into the original function to get the y values. And the order, you'll notice I listed them in, I started from the leftmost to the rightmost. It's just nicer to read that way, but you don't have to. Here's another example of working with a graph and trying to figure out the intervals of increase, decrease, and concavity. So again, one of the first things you should do is take the derivatives, which are 4x cubed minus 2x, and the second derivative, which is 12x squared minus 2. Now your possible min maxes. Set the first derivative to 0. Use your calculator. You can use the second derivative test on them. again, I'm just putting each of these x values into the second derivative. The first one gives me approximately 4, the second one gives me approximately 4, and the last one gives me -2. So again, greater than 0 for each of these, less than 0, which means we have a min, and a max. Our inflection point, again, are the second derivative to 0, which gives us x1 is 0.41, x2 is -0.41. Now, if you were to graph this, which I find helps quite a bit with the intervals, you basically have some kind of W shape. And then it helps sometimes to list out the x values of each. So this would be x equals 0, your max. You have x equals -0.71 here, and x equals +0.71 here. And then you have your inflection points in here. This one's the -0.41 and the +0.41. Now we can use the min and maxes for our limits on our intervals of increase and decrease, and then we can use our points of inflection for where concavity changes. So your intervals of increase are -0.71, less than x, less than 0, and x greater than 0.71. Our intervals of decrease are x less than -0.71 and 0 less than x less than 0.71. Our intervals of concave up are x less than -0.41 and x greater than 0.41. And then our concave down interval is -0.41 less than x less than 0.41. Now let's take a minute and go through these in a little bit more. So interval of increase. From here to here it's increasing. That was our first interval. And then above 0.71 it was increasing. So that was our second interval. For decrease, less than -0.71 was a decrease, and between 0 and 0.71 it was a decrease. And then if we look at concavity, concave up here and concave up here were these two intervals, and concave down here was this interval. Okay, now let's do a couple of optimization examples. Here we have a fencing problem. Fencing problems always involve the formula of area and a modified perimeter. Now area is just length times width. So let's call these three fences width, this fence length, and we have an existing fence on the other side, so that will definitely modify our fencing formula, but area never changes. It's just length, width is 400, and I'm going to isolate L to 400 over W so that we can substitute it into our fencing formula. Now fence, here we're fencing 3 W's plus 1 L. Again, we can simplify to 400 W to the 3W plus 400 W to the -1. Just substituting the L back in. Now we take the derivative with respect to W, which is just 3 minus 400 W -2. Now for optimization, we always set our derivative to 0 and solve. And we get a W of plus or minus 11.55. But the negative doesn't make sense, so we're going to rule out the negative and only worry about the positive. We can use that to then calculate L. Which is approximately 34.63. So therefore we have a field that is 11.6 meters by 34 11.6 meters, with the width being the 11.6 and the longer side that's parallel to the existing fence being 34.6 meters. Here we have a tin can question. Now there's two variants on the tin can question. There's the ones where I give you the amount of metal and you maximize the volume, or there's ones like this where I give you a volume and you have to minimize the amount of metal. So we're given the volume, so we know volume of a cylinder is pi r squared h, which is equal to 600 in this case. I'm going to isolate h. And then we know the surface area of a cylinder is 2 pi r squared plus 2 pi r h. I'm going to substitute the h in. And then I'm going to simplify. So the 2 times the 600 is 1200. Pi's divide out, and we're left with 1r in the denominator, which is r to the negative 1. We take our derivative with respect to r. We set equal to 0. And solve for r. And we get about 4.57. And then we can plug that back in to get our h. Which is about 9.14. So therefore we need a radius of 4.57 centimeters and a height of 9.14 centimeters. Our last example is working with the strength of a beam. Now we have a circular log and we're cutting a rectangular beam out of it. Now for these, we're only going to look at the cross-sectional area of the log. Now we know the diameter of the log is 60 centimeters. Now you'll notice I put it from one corner of the rectangle to the other, and that's also equal to your diameter. Now we are working with width and depth, so the width of the rectangle and the depth of the rectangle. We have a right triangle, which means we can use Pythagorean theorem. So w squared plus d squared equals 60 squared. Then we're also told the strength of the beam varies directly with its width and the square of its depth, or S equals kW squared. Don't worry about k, it's just a constant. It'll actually divide out later, as you'll see. But right now we have two variables and we have two equations. We can rearrange this one so it's d squared equals 60 squared, which is 3600, minus w squared, and plug it in to this one, giving us, which we can simplify. Now we can take our derivative with respect to w. Set it equal to 0. And start solving. Here we can divide both sides by 3k. And as I said, that k divides out. Now w will be the square root of that. But we know that w has to be a positive value. It's a length. So w is 34.64, at which point we can go up here and we can solve for d using the square root of 3600 minus w squared. And we are going to get approximately 48.99. So therefore, we need a width of 34.6 centimeters and a depth of 49.0 centimeters.